right. So today's problem is subtree of another tree. Surprise, it's the tree problem. I think this is the last of the easy problems we're going to do for trees, and then this does kind of piggyback on yesterday's solution. So if you're not already familiar with same tree or same binary tree, that would be one to check out first. We'll do a brief overview of it today because it's sort of a core part of the solution for the next problem. It's not a terribly tough one. I'm kind of spoiling the solution already, so apologies about that. It's up on the screen already. But yeah, let's talk through the problem for today, and then we'll talk about how it relates to our previous solution. Okay, so here's the prompt. It says, given the roots of two binary trees, root and subroot, we want to return true if there is a subtree of root with the same structure and node values of subroot, and then false otherwise. So basically, if subroot is a subtree of root, we'll return true. If it's not, then we'll return false. And then they clarified, just to be specific here, what exactly they mean by that. A subtree of a binary tree, oh god, this is going to be so tough to read, is a tree that consists of a node in tree and all of this node's descendants. The tree could also be considered as a subtree of itself. I think this is best explained by just looking at some examples here, because the overall idea is actually pretty straightforward. Basically, if we can find this exact structure right here somewhere in the other tree, then we would consider it a subtree. So in this case, we have 2, 4, 5, and then nothing below that. And you can see that you can find that structure visually right here. Obviously, we still need a way to programmatically find or confirm that, but you can tell by looking at it what we mean by that. Okay, and very similar but slightly tweaked example here. You can see in the first one we did find that subtree, and the only change in the next one is that the main tree this time has an extra child here on the left, and this one returns false. And the reason for this is, although it's not really shown to us visually here, there is an additional part of the structure that we kind of can't see, and that is the none nodes at the bottom here. So 4 and 5 both have none for their left and right children. By contrast, over here we have 2, 4, 5, and then this one, or for this particular part, that 4 node has an actual left child, which is not the case in the subtree on the right. Okay, so all that to say, if the children of the leaf nodes are not the same, so if there's additional structures somewhere, we would consider that no longer a subtree, and we would return false. Okay, and then some constraints. Not a huge deal here because we have to deal with them all anyways, but the number of nodes is between 1 and 100. This at least confirms to us that there will be one node in each tree, at least. And then the values will be between negative 100, positive 100. We won't be manipulating those, so no huge deal there. All right, so let's start actually by talking about, GoodNote's just updated, so let's see if it does something weird today. Great. Okay, so the problem yesterday, here's the diagram that we looked at. The problem yesterday was to confirm whether or not two trees are just the same tree. Now, what we do here is we recursively say, hey, for any particular node in the tree, we want to ask ourselves, is the value the same as what it is in the other tree? So we're comparing two nodes that are corresponding. Are the values the same? And then the question we ask is, are the left subtrees the same, and are the right subtrees the same? Okay. If that holds true for every single node in the tree, then we can confirm, yes, in fact, these are the same trees. So that was a recursive definition for this. We also need some base cases that just tell us, when would we know for sure that two trees are or are not the same? So if the two nodes that you're looking at are both none, that would be one scenario where we could say, hey, these are two identical trees. They're both nothing, but they're still identical, right? So that would be what we consider a success-based case. That means we can stop and say, yeah, from here on it looks good. Okay, so there's lots of failure-based cases, and the failure-based cases are if the two values are not actually the same. So for example, if this was a 2 here, we would confirm immediately these are not the same tree, right? Because their values don't correspond. And then outside of that, we have these two scenarios where either we have a node in one place and not in, well, yeah, basically that. We have a node on one tree, but we do not have a node on the other tree. And that's a scenario like this one right here, where one of the left children is none, but the other left child is an actual node. And that's actually the like kind of the false scenario that we encountered right here, where there's a child here, but there's no child here. And that would confirm to us that they're not really the same tree. Okay, and the logic for that is actually pretty straightforward. We'll basically just translate these exact base cases into like conditionals. Yeah. Okay, and so the difference for this problem is we're not just trying to compare two trees directly, we're trying to confirm if this tree is somewhere in here. But a way we could rephrase that, or a different way we could think about it, is basically, hey, is there any root node over here, or is there any node over here, where that subtree is the same as this subtree? Right, so basically for every node here, we'll have to traverse the whole tree and just try and figure out, hey, do any of these nodes completely contain that subtree? Okay, and that's pretty much it. Now, yesterday we used some AND logic to say, hey, everything needs to work properly or else it's not the same tree. We're going to kind of combine that now with OR logic to say if any node in the tree works this way, if any node in the tree over here is the subtree, then that's actually a win for us. That means that the subtree is contained in the main tree. Okay, and on the other hand, if we get through the whole tree and we never found the subtree, then we can confirm that it's not present anywhere, and we can return false. Okay, now one thing you might consider at this point is, hey, it seems kind of like wasteful to repeatedly do the whole same tree algorithm. Shouldn't we have some like additional checking or some additional logic to get rid of some certain cases? Well, the same tree logic fails immediately if we don't match like from the top to the bottom, right? So as soon as there's a failure, we can just move on to the next candidate. There's very little like wasted effort, so to speak, because like the function will just stop as soon as it fails. So we can kind of rely on that immediately, like to compare, for example, like from the root to this subroot. We immediately know that it doesn't work because the values are different, right? So we won't do the whole like tree of recursion. We will just compare those, find out it fails immediately, and then go on to the next guy. All right. Okay, so let's start by, and there's a few ways for us to like structure this, but let's start by just implementing the same tree logic from yesterday. I'm actually going to put that into its own function because we're going to use it recursively, so we want to be able to like call that same function. So we'll say def is same tree, and we need to feed that a root. Well, I'll actually use the same like terminology or syntax as yesterday. We'll call one of the roots p and one of the roots q. And let me split screen real quick so we can get this up. Okay, so we need to capture these scenarios here. Ooh. And we want to do it kind of from the most nones to the least nones, if that makes sense. So we'll start with the success-based case here to say if not p and not q. This is good news for us. That means we hit none at the same time on both trees. We can return true. Okay, on the other hand, if not p and q, so none on the first one but node on the second one, that's a failure. Or node on the first one and not on the second one, that would be a failure. Okay, and finally, if p's value is not the same as q's value, that would also be a failure. Okay, and we do kind of want to do it in this order because well, I mean, these ones are kind of interchangeable because we're just checking if there's something there, but we definitely want to do the value checking last because we first want to check, like, do we actually have nodes in both places because if not, we can't call value on them, right? Or we can't check their value member. Okay, and then now assuming we get to this point, we now know that we have two nodes and their values are equal. Okay, I'll get rid of the notes here. Okay, and assuming that the two nodes look good so far, now we need to make sure that their left subtrees and their right subtrees also match. So we can return is same tree p.left with p.right, or sorry, p.left and q.left, and is same tree p.right q.right. Okay, so we're saying go ahead and make sure that the nodes themselves work in terms of being the same tree, and then go ahead and make sure the left subtree and the right subtree work. Right. Neil was here a second ago. I'm not sure. He has a habit of popping in while I introduce the problem and then just leaving. I'm not sure why. Love that guy, though. Okay, so this is yesterday's problem in a nutshell. Again, what we're going to do here is we're just going to go through each node and check, hey, starting from this node, is this the same as the subtree? And if not, we move on to the next guy until we've exhausted everything. Okay, so how are we going to do this? It's a great question. We could describe everything with one single word. No, we can check if the current root is the same as the subtree. So we can say if is same tree root subroot, then we can return true. This means that this is the place where it is the same tree, and we'll return that all the way up. Now, let's see, actually. If that fails, then we can say, hey, is the left subtree the same? Okay, so yeah, you know what? We'll comment this out a little bit later. We'll get through the code first, and then we'll do some comments on why it works this way. So we can say if is same tree root.left subroot, or is same tree root.right subroot. So I guess we can actually combine this and say is same tree root subroot, or is same tree root.left subroot, or is same tree root.right subroot. And let's actually organize this a little bit better. I'm going to put this right here. And we'll put these on their own lines just so that we don't have this insanely long, like, running line. So if any one of these works, we can return true. Otherwise, we'll return false. Is that it? Oh boy. Something feels the tiniest bit off here, which is... Well, no, these, yeah, same tree has its own base case, so actually this very well might work. Let's take a look. Great, yeah, she works just fine. Here's what has me thrown off here, and we were sort of forced into, well, not forced into this, but the terminology I've used is a little bit icky, shall we say. And that's because really what this... okay, actually we sort of were forced into this because we do have to use their naming convention here. The function they've given us is called isSubtree. It would maybe be more accurate to say like has subtree here, because we're not saying that the two trees have to be the same. We're just saying that it has to be present somewhere, right? So I would like if this was called has subtree, just because you can see that the main body of the function here is trying to say if either the root or if the tree is present at the root or in the left subtree or in the right subtree, we want to return true. And otherwise we return false. So if this was up to me, I would probably rename the overall function here. But the logic still holds for us to say either the root is the same as the subtree, or the left child is the same as the subtree, or the right child is the same as the subtree. And that'll be the same for all of these nodes. Like, it's the same question. Either the subtree is here, or maybe it's on the left, or maybe it's on the right. And if none of those places have it, then we return false, right? So, we'll, assuming we don't find it early, we'll go through every single one of these nodes and ask that same question. If nobody ever finds it, we return false. But if any of them find it, that's why we use or here, we return true. Okay, did I submit? I guess let's just make sure this works. Oh no, oh no. Mess. Now, not me failing the easy problem. What have I done wrong? Somebody help me. Same tree root dot left subroot or is same tree root dot right? Ooh. Now, why in the world would that not work, actually, now that I think about it? P value false, return is same tree P dot left, Q dot left, P dot right, Q dot right. Huh, I really thought that was going to be it, y'all. Let me think about this. Because the root... Okay, wait, let's just take a look here. Oh, just kidding, there we go. We returned false when we should have returned true. I can't think of a reason why this wouldn't work. The only thing I can think of is that I've got the setup of root subroot, root dot left subroot, root dot right subroot, return true. I'm trying to think about why, if I have any logical errors off the bat that I can tell. If not, we'll do some debugging here to figure out where it went wrong. So let me just chew on this for 1 second. By all rights, I feel like this is supposed to work. I'm not gonna lie. Well, I guess, you know what? The only scenario I can think of... Wait. Why would this return true? We are looking at subtree of another tree, which, let me make sure that I understand the premise of this correctly. Yeah, no, I'm pretty sure I get exactly how this is supposed to work. Because we would say... P dot Q return false. Yeah, this all looks good here. Same tree root dot right. The only thing I can think of is if we I feel like that should have worked. How does the if work? It tries all of these. So is same tree. Oh, my bad. I understand. Sorry, I'm only calling is same tree, which is not what we want. I should be calling is subtree right here, because we need to recursively search the left and the right subtrees. So the reason it worked early on is because the subroot was present at the first layer of recursion. So that's why the first test cases work. First test cases. But really, we should be doing this so that we can look through the left and the right subtrees, right? And then, okay, yeah. So for the root itself, we're going to check, is this the same tree as the subtree? Okay, if it's not, then let's try the whole left subtree and the whole right subtree. So I was just calling the wrong function here for the recursion. Oh yeah, self dot is subtree here because it's class function. Oh. I really did not like that. Oh, okay. And then self, okay, so is subtree, ugh, this is annoying. Okay, so we're gonna have to split this because is subtree itself currently does not handle none nodes. But shouldn't that be fine? Oh, no, because you can't call is subtree on a none node. Well, hold on, let's think about this. So when we get to the, I wonder if there's like a more elegant way to do this. Self dot is subtree root dot left and subroot. We should still be able to pass none. The problem is, okay, here's the problem, is we get here, and this works just fine because we have a none and a node, and that's not going to work. But then we go into this one, and we try and call like none.left, and that doesn't work, right? Okay, so we need to do some null checking here, and I'm going to split this now into a few different conditions. So we can say if is same tree root subroot, return true. Elif root dot left and is self dot is subtree root dot left subroot, return true. And finally, elif root dot left or root dot right and self dot is subtree root dot right subroot. Ooh, we return true. Okay, so this is just doing null checking to make sure we actually can access something on the left node. So if there's a none, we just don't have to do it because there's no way for a none node to be the same as a tree with nodes, which, by the way, from the constraints, they told us there's always going to be at least one node in the subtree. Okay, so that finally should do us for. There we go. All right, so the logic has been correct from the beginning here. There was some syntactical issues, but we lived. Great. Your question did help, and the if definitely was where we needed to look. So yeah, the overall, well, so again, if you weren't here for yesterday's problem or you don't know how to do is same tree, we stole that logic from yesterday. Pretty straightforward. And then for the actual recursive part of this, we're going to say, hey, if the current root matches the subtree that we're looking at, then we can return true. Otherwise, we need to ask the whole question on the left subtree, if there is one, and the whole question on the right subtree, if there is one. And if we never get a match, we return false. Great. Okay, and that's that. Perfect. Slightly longer than I was hoping. I love making mistakes for some reason. But not too bad overall. Chillin'. Okay, y'all let me know if you have any questions, but otherwise we'll call it a night. I'm gonna end the recording here regardless.